Hi everyone, thank you for coming. Continue today with security at application layer. So we'll talk maybe about one of them, we'll keep the other one for you to read. So the same idea. So as we said last time, if you remember, we always start from the OSI reference model, right? You bring this closer. Okay, so in the OSI reference model, we have about 7 layers. Okay, so we start with the physical, right? Then we have the data link. Then we have the network, transport, then the application. Right? So the data, it goes start from the application. Let's say it's like HTTP application, okay, when it issues. So usually at each layer you'll have, like you'll have the packet, okay. It has data, whatever the data is, okay. In this case, if you're using HTTP, HTML code, for example, it will be, and there is header, right? Let's say the header application. So the whole thing will move down. Will move down. Whole thing here will move down here, and we're gonna add. Okay, we're gonna add one more header. For example, header add transport, right? Okay. The whole thing will move further down. Okay. Okay. And we'll add. So this, the whole thing in here will be added. Okay, we'll add another header for example, at the network layer. Up to down, also we go down, okay, and we add, for example, a header, at the data link layer, okay, MAC layer, for example, and so on and so forth. So as we go from one layer to layer, the data frame becomes bigger, right? Becomes bigger, right? All right. So. We need to provide security, so it could be at each layer we change the data to secure it in terms of authentication, in terms of encryption, for privacy, for different things, right? So you could have security at the application level, and you could have application security at the transport level, okay? Okay, and you could, so for example, in the application level, there is 2 examples in here, PGP for the mail. Or mine, right? Yeah, it's mine. Okay. Okay, we have, for example, HTTPS secure HTTP, right? in the transport layer to have TLS, for example. Okay, in the network layer you have IP, secure IP for tunnel, and so on and so forth, right? So you could have no security at all in all of the layers. You could have in any one. You could have in any 2. You could have in any 3. All right. However, the security is implemented at each level is different. There's different protocols, different way of doing it. So today we're going to look at the security at the application level, next class maybe in the transport level, and then on the network. Okay, that's what we'll be talking about. Okay, so maybe today we'll look at PGP just to understand. As before, now we are expert. We could take a look at any protocol. We could read it. We could understand how they implement it because we have the background, right? So when we start talking about symmetric encryption, we spoke about DAS, triple DAS, double DAS, AES. Okay, done in different ways, but you understand. Then we spoke about asymmetric, where we have 2 keys, right? So we spoke about like 5 or 6 different algorithms. When we talk about digital signature, different algorithms, right? Same thing in here. There is many application level algorithms that could be used and vary. Okay, so let's take a look at PGP. Pretty good privacy. PGP is a pretty good privacy. So we're going to explain the general structure of an email application program, because the PGP and MIME is used for email. To discuss how PGP can provide security services for email, and then we discuss how SMIME can provide security services for email. If you have time, we'll go over it, or I keep it for you to go over it. I mean, it's explained well in the textbook. And then define the trust mechanism involved with PGP and SMIME, and to show the structure of the message exchange in PGP and SMIME. So let's focus on PGP today. Okay, pretty good in privacy, just to get an idea. So PGP is used to secure emails, right? So the first thing is first. So we have to understand how emails work, right? So we have to understand how the system works. So we're going to take a look at the email architecture, and then we'll talk about email security. So for the email architecture, as you see in here, for example, so you have user agent, and you have message transfer agent. So Alice would like to send an email to Bob, so it has a user agent and message transfer agent. All right, so Alice will send them email. The email does not go directly to Bob. It goes to something called mail server. Okay, mail server. So it will go to the mail server. The mail server will queue the emails somehow in the message transfer agent and server, message transfer agent server, and message transfer agent client. All right, it will be saved, and one of the clients will take the message from the queue and forward it over the internet. Again, the message does not go directly to Bob, it goes to a server, mail server. Okay, so if you have a Gmail account and you have UB account, there is mail server for Gmail and mail server for you. So the server will receive it, and then after that it will be accessed by a message access agent, and it will be sent to Bob through LAN or WAN, depends on how is it configured. So basically we have a sender system or a reception system, and this will have message transfer agent, and this has message access agent to access the message. So it involves two servers who are receiving the data. All right. All right. So the MTA, the message transfer agent client, it's a program that which is a push program. The client pushes the message when Alice needs to send it. The MAA client, which is in here, MAA client, is a poll program. The client polls the messages when Bob is ready to receive it. So you don't have to be in the front of your computer to read your email. If your email is shut down, there's no problem. It will be saved from here. When you log into your email client, whatever it is, whatever you use, it will be pulled, okay, to your screen. All right. So let's talk about the security. So the cryptographic algorithm. So in email security, the sender of the message needs to include the name or identifiers of the algorithms used in the message. So for example, if you encrypt your email using AES, so this information has to be included in the email, that the recipient will be able to know which protocol to use, right? Because you have the option to encrypt it with different algorithms, right? So this is a very important. You could use certificates, so it is obvious that some public key algorithms must be used for email security. Okay, because you're gonna encrypt, for example, with a private key, with a public key of the recipient, and then the recipient will read it with its private key. All right, so because there's two people, and then we could use a public key. Okay, So for the secrets in email security, the encryption and decryption is done using a symmetric key algorithm. Symmetric key, one key, shared key. But the secret key to decrypt the message is encrypted with the public key. So we encrypt the message with the symmetric key. But the key itself is encrypted, okay, with the public key of the receiver. So the only person can read it is the receiver. So the receiver, when receives the message, what is the first thing? Has to read the key. Then use the key to unlock the message. So we're going to use symmetric and asymmetric. Symmetric for the message, asymmetric for the key. Okay, clear? Okay, symmetric for the key with the message. Alright, so that's generally how we do it, right? Alright. So let's talk about PGP. PGP, pretty good privacy, can be used to create a secure email message or to store a file securely for future retrieval. So either to send a secure email or to save a file secured. So you could encrypt it, use PGP for that. So we'll talk about scenarios, key rings, PGP certificates, key revocation. Revocation, yes, extracting information from rings. You have a ring, you can extract information from it. PGP packets, okay, and the PGP messages. PGP messages. So, plain text in here. So, in the plain text message, Alice could send the data as plain text over the internet. So this is completely not secure. Anybody could read it. So anybody could snoop and the spoof can read the data as a plain text, right? We could do that. Maybe most of us do that. I don't know. Okay. And we're talking about security at the application level. That's not. I mean, if you don't use security at the application level, we might have security at these levels, right? So it's not necessarily that if you don't have application level security, okay, that what we are talking about, the data in here. Because it's encrypted or not. So it could be not encrypted, but when it goes to the low level, it would be encrypted. Alright? Or we could use a message integrity. What is message integrity? We don't care about the privacy of the message. So we use encryption to do what? To create privacy. But I don't care about private messages. I care about the message is integral, no changes. I want to know the message did not change. So if I send you an email that you have a quiz next week, it does not need to be private or secret, but you need to know nobody changed anything in the message, regardless of the information. That's what we call it, message integrity. So what we have to use, authenticated message. How we do that is very simple. We have learned that Alice would like to send a message to Bob. So this is the data, all right? And what we create a digest, like a hash function. You know what digest? We already learned that. Of the message, right? So Alice and Bob will agree in one hashing function to create that digest, all right? So we could create a digest, all right? But you know, somebody could create similar digest from the similar data after changing the data. So I don't need to keep the data protected. I can encrypt what? The digest itself, which is a small packet, okay? Small data, okay? With what? With A, which is, you know, it's a digitally signed with Alice's private key. So Alice will sign it with her private key, right? It will be received by Bob. Bob has Alice's public key. So could check what is the first thing has to do, Bob, to generate the digest again. Number two, to unlock the digest, compare the two digests, the received one and the checked one. If they are the same, then the message is integral, has no changes has happened. If the messages are different, that somebody has played with the messages. So, right? Alright, so in this scenario, we were focusing on the message integrity, how to make the message integral, no privacy. Then you could have compression, because when you compress the data will change completely, right? You compress the data. So a compressed message, so for example, so you have the data in here, you compress it. Then you generate a digest, not from the data itself, from the compressed data. So it's extra level of security because the data transmitted in the wire is not a regular data. It's a compressed data. So it looks completely different, right? Okay. And then we have to digitally sign this with Alice's private key. Bob will receive it. What is the first thing we'll do? We'll generate the digest, compare it with this digest. If it's good, then it's good. Then after that, they uncompress the data. There's different algorithms for compressing the data. They have to agree in one compression technique. All right, that's it. They have to agree on that. So both of them, they have to agree in one hash function to create the digest. Both of them, they have to agree in the compression technique, one algorithm to use, and they're gonna use the public key for what? Just for integrity, to make it like integrity. So this is what we call it, compressed messages, compression.
So Professor, this after, Bob received the data, so Bob will receive the compressed data or it will get the regular data?
We will receive compressed data.
Compressed data.
Because that's what is in the wire. But the Bob knows how to decompress it. Because they know what technique used for compression. All right. Then we could have confidential. So again, let's go back in here. So in here, plain text, there is no security. In here, just we worry about the message integrity. In here, compression with message integrity, and you could have confidentiality with one-time. We spoke about how to generate one-time session key last time, right? Diffie-Hellman is one of the examples, if you remember. So a confidential message. So in here, what will happen? Alice's private key and Bob's public key. So what you'll do? So you create a digest and you encrypt the digest with what? Okay, when you create the digest with digitally signed with Alice's private key. So this is for integrity. And you take the message, you compress it. You join them together, and what you do in here? You encrypt with shared session key. You encrypt with a shared session key. And in the last lecture, we learned how can we generate the shared session key, right? And what you add to it, the session key, the shared session key. Why you have to add it? Because Bob has to use it to be able to open this. But if you send it as a plain text, everybody will know the shared session key. So for extra security, what you do with it, you encrypt it with Bob's public key. So the only one can read the shared session key is Bob. We use his public key to encrypt it. Bob is the only one can know how to decrypt it. Okay? So that's what it is. So number one, we create the digest with algorithm agreed upon between Bob and Alice. Number two, the digest, we don't send it as a plain. We encrypt it or we digitally sign it with Alice's private key. And Bob could use Alice's public key to read it. Then we compress the message. We put them in one box together. Everything what we do with it, we encrypt it with the shared key. Now I have to send the message with the shared key to who? To Bob. Bob needs to know the shared key to be able to unlock it, okay? So we send the shared key. If I send it as a plain text, then anybody can read it. So what I do, I encrypt it. What I do, I encrypt the shared key with Bob's public key. The only one can read it is Bob with his private key. Right? Very secure. So in here, what we guaranteed in here, the data is compressed, the data is integral, the data is confidential, okay, the whole message is encrypted, the shared key is encrypted, everything is secure, everything is nice. So that's what they call it, confidentiality with one-time shared session. All right, so another service provided by PGP is code conversion. PGP uses Radix 64 conversion. It's one technique is to convert. We'll take a look in a second, but we convert the data to Radix conversion. Okay, like you could convert from ASCII to EBCDIC. It's like a way to convert how the data is represented. We call it Radix 64. So we'll take a look at it in a second. So most of the email system usually allow the message to consist only with ASCII or ASCII characters. Okay, to translate other characters not in the ASCII set. So, for example, if you are using Hindu letters, there is no ASCII or Arabic letters. Okay, so you have to have different. So PGP uses Radix 64 conversion. Each character to be sent after the encryption is converted to Radix 64 code. Okay. Anyways. Then segmentation, PGP allows segmentation of the message. What is segmentation of the message means? After converting to Radix 64, we make each transmitted unit the uniform size. So, like you divide the data into segments with a uniform size. Maybe the last one is a little bit short, maybe do padding, okay, but it will be segments. So one email could have 10 segments, another email could have 5 segments, so you try to divide it into segments. They call it segmentation. All right. So, as you see in here, what do we need in here? I mean, here, what do we need? We need private links, we need public links, and we need public keys, private keys, and shared keys. So myself, for example, Allison here needed Allison in here needed, for example, in here the private key, her own private key. In here, what does it need? For example, the public key of Bob. Okay, so if I need to send you an email, I have to know the public key of all of you. So I have to have ring with all the public keys, right? Right? If I have to have access to many offices in this building, I have to have a ring with a key for each office, right? Okay. What if I know 1 million people? How can I maintain a ring of public keys for 1 million people? Right? So it's not, you don't want that for every email you send, you're gonna spend half an hour to look for the public key, right? You have to have a ring, right? Ring. So we're gonna talk about the rings now, how to have rings. You understand the idea? All right. So security has a cost, as you know. So key rings for PGP. So for example, Alice's ring, she will have a private ring, and has a public ring for public keys for other people. All right, and she will have a private link for her to communicate with other people. So I have a private key to communicate with her. It's one key. To communicate with him is another key. Okay, which is a pair of keys, right? Each private has a public. But for other people, I have to have their own only public key. So Bob, for example, will have private link which has pair of pair of keys. So this, for example, pair of keys to communicate with Osif Mahmoud, Professor Sayyid Mahmoud. This is a pair of ring to communicate with Omar Abu Zagla. This is to communicate with Dean Tariq Sot, right? Pair, all right. It's my keys, but one of them is public and one is private. And then here the public key with many other people. Same thing with the Bob ring, Ted's ring, or Jim. So we have to create like a box with keys. right? You could say, why I have to have a ring for public-private? Let me have one public, one private, I share it with everybody. This is not very secure, right? Okay? You got the idea in here? You are all good? Okay? So, so for the key rings, so you're gonna have a private public key, then you have the public keys of other people as you see in here. Alright, so the question, how we share these rings, right? How we share these rings. So, in the PGP algorithm, for the public key algorithm, okay, for the public key algorithm, so ID 1, RSA, encryption, or signing. So in the PGP, there's different functions you could do. You could choose. If the ID is 1, then you are doing encryption and or signing using RSA. RSA is asymmetric algorithm that we have learned, right? The first one we have learned. If the ID is 2, then we're using RSA for encryption only. Doing encryption. 3 RSA for signing only. So this is encryption signing, encryption only, signing only. 16 it using Al-Jamal for encryption only. 17 using DSS, another algorithm which we studied, right? 18 reserved for elliptic curve, reserved for ACDS, one of the algorithms we have studied. 20 Al-Jamal for encryption and signing. 21 reserved for Diffie-Hellman. We learned at last class. You could generate session key, right? And 100 to 110 private algorithms, different algorithms you could check. So with PGP, okay, both sender and receiver have to agree in the ID. So if you send the ID one, that meant the receiver will know that the receiver and the sender will know both are using RSA for encryption and signing. Right? You have to know which algorithm you're using, right? You could use many, there's so many different algorithms, right? Now, this is for public key algorithms. For symmetric key algorithms, okay, ID 0, no encryption, 1 idea, 1, okay, 3 triple this, 2 triple this, 3 cast 128, 4 bluefish, one of the algorithms we did not study bluefish, 5 safer SK 128, and so on and so forth. Alright? For hash algorithms, okay, where are we using the hash algorithms? Here. How are we creating the digest? By hash. Alright? Who gonna create the digest? Who will create the digest? Tell me. Who's creating the digest?
The hash.
The hash function, but who? The sender or the receiver?
The sender.
No. Who gonna create the hash? The digest. Who gonna use the hash to create the digest? Can you tell me who's doing that? To create the digest, we have to use a hash function. Who's doing that? The sender or the receiver?
Sender.
Receiver.
Who said receiver? Receiver. Who says sender? A third opinion.
Both parties.
Both parties. Because the sender has to create it,
Oh, yes.
and the receiver has to recreate it to compare.
Compare, yes.
So both parties need to know which hash function we have to use. They have to use the same, right? So as part of the PGP, you have to share this information, what kind of hash. If it's 1, then we are using both MD5. If it's 2, we are using SHA-1. If it's a 3, this, 4, this, 5, this, so on and so forth. Right? So both has to know that. All right, thank you. You came late, but I'm not sure how you answered. You're clever. Yeah. For compression, the same thing. Who's doing the compression? Who's doing the you? You came late. Who's doing the compression?
The sender.
Yeah, take a look in here and tell me who's doing the compression.
The sender.
The sender?
Yes.
Why then the receiver needs to know the compression algorithm? Huh?
They both have to do it?
Both of them do it? No.
No. Yeah, because.
No.
But doesn't it have to uncompress the message?
They have what?
Uncompress the message?
The sender will compress it.
Yeah.
The receiver what will do?
Decompress.
Decompress.
Yeah, decompress.
Decompress. Then they have both to know which compression technique is used.
Yeah.
Good. But not both doing the compression. One is doing the compression, the other doing the compression. In terms of hash, both of them are doing the hashing and then comparing, right?
Professor, I have a question. Like in the previous figure, like the digest is encrypted with Alice's private key, right?
This
Yeah,
one?
here, the digest is
Yeah.
it is encrypted like it's
With
secured
Alice is a
with
private
pri-
key.
Like to look at the data, like Bob should know the private key of the Alice.
Yeah, but remember here what we are doing? We're signing.
Like,
We are. The idea here is to sign it, not to keep it private. So Alice will sign it. How we sign things? With our, which is private key. Okay. Then the other party will be able to check the signature with the public key. So in here, even A, you see A in here, digitally signed.
so like if
We are not encrypting. Just a second. We are in here. We only signing. In here, what we are doing, encrypting. So we don't care about keeping this private. We care about making sure it's signed by the right person.
Authentic.
like what I thought is like if he's sharing his private key with everyone, then what is the purpose of then there won't be
He's not sharing the private. Remember, there is a public and so Alice has a public key and a private key. So Alice using her private key. Nobody knows the private key except Alice. Now this we're gonna go to where? To Bob. Bob could use the public key, which is public anyways. So you don't share your private key with anyone. She's not sharing it. She's sharing the public key. But remember that in asymmetric that we use public and private the same way together. You got it? Yeah. Thank you for the question. All right. So for compression, so 0 and compressed, 1 zip, Z left, and so on and so forth. There is different techniques for compression. They have to agree in what compression that they're gonna do. Remember we spoke about X509 certificates last time?
Yeah.
Last time we spoke, this is a standard to create certificates, right? Right? So protocols that use X509 certificates depend on the hierarchical structure of the trust. Hierarchical. We spoke that last time. So, you know, a person will trust a person, trust a person, you know, it will, you know, how you inherit the trust, right? So X509, there is a single path from the fully trusted authority to any certificate. So, okay. So PGP certificates. PGP certificates. So in PGP there is no need for CAs. What is CAs? Certification authorities. Okay, anymore in the ring can sign a certificate for anyone else in the ring. So anyone in the ring can sign. So for example, if we have a ring in here, okay, all right. So you put a person in the ring, then you trust him. You could sign for anyone. You could sign for anyone because you put him in the same ring, then he's trusted. All right. You don't have to go to third party outside because certificate authority. Okay. So usually with the certificate authority, what we do that when we sign, we send the signature to the third party. Okay, please sign for this, and they send the signature to the person, right? Like a middleman.
Like
For
trusted
here,
center.
huh?
Trusted center.
A trusted center, right? In here, because they are in the part of, if you are in the same ring, you could sign for anybody. Okay? Okay, so in BGB there can be multiple paths from fully to partially trusted authorities to any subject. Okay, you could go through, we'll see an example now. So, trust and legitimacy. The entire operation of PGB is based on introducer trust, the certificate of trust, and the legitimacy of the public keys. Three things. Introducer trust, certificate of trust, you could, if you have a certificate, you could trust that person, or by the introducer. If there is an introducer who you trust, introduced another person for you, then you become trusting. So if you trust me and introduced him to you, then you trust him. Because you trust me, I introduce a third party, then you're gonna trust both of us. Okay? Introducer trust, certificate of trust, and legitimacy of the public keys. All right. So introducer trust levels. When you look at the introducer trust levels, so we don't have, of course, central authority. Okay, it is obvious that the ring cannot be very large if every user in the PGB ring of users has to fully trust everyone else. Even in the real life, we cannot fully trust everyone that we know, right? So to solve this problem, PGB allows different levels of trust. So the number of levels is mostly implementation dependent. So Microsoft use different PGB, Unix different PGB is implementation. But there is level of trust. Okay? So the number of levels is mostly implemented is implementation dependent. But for simplicity, let us assign 3 levels of trust to any introducer: none, partial, full. So you don't trust, you partially trust, or fully trust. Okay? Again, this is for simplification, you know. Okay? Okay, so the introducer trust level specifies the trust levels issued by the introducer for other people in the ring. For example, Alice may fully trust Bob, partially trust Anne, and not trust John. You could trust a person, partially trust a person, and not trust a person. This is there is no mechanism in BGB to determine how to make decision about trustworthiness. Just you have to decide yourself. You trust, partial trust, you don't trust, and all of that. Okay? So in here what we have, format of a private key ring table. So this is a private key ring. You're gonna carry with you a private key ring table. So you're gonna have your own keys, pairs of all keys. So with her, I have a pair that I use with her. They are my public key and private key, but I use this pair with her. I have another pair to use it only with him. Another pair I use it with third person, so forth. So you have the user ID, the key ID, the public key, and when I save, I save the encrypted private key. So, you know, it's saved encrypted. Because if somebody knows the private key, that's a problem, right? Public keys are public, and then the timestamp, because it could have a life when you issue it. So you issue a key for a month. After a month, needs to be renewed. You throw this pair, and you get another pair. All right. So that's how it's the format of a private key ring. So it has the user ID, the key ID. So the user ID is usually the name, the email address, for example. So what's the user? It's like the email address. Okay, and the key ID is a unique number. Okay, so the key ID for each pair first, it could be the first 64 bits of the, it could be the first 64 from the public key. So for example, this is the public key. You take the first 64, okay, and you give it as a user ID. Alright? Could be different implementation. The public key was public key, and then the encrypted private key, this column shows the encrypted value of the private key in the private key public key. Although Alice is the only person accessing the private ring, PGP saves only the encrypted version of the private key. We will see later how the private key is encrypted and decrypted. So we know in the key, the PGP, even the private key, you only the person know it. Still, for extra security, you save it encrypted. Got it? You save it encrypted. It's exactly like you have your passwords. You save it in a file in your computer. So stupid to do that, right? You put it in a file, but this file has to be encrypted. Because if somebody steals your hard disk drive, you'll get it, right? But if they steal your hard disk drive and the file that has your password is encrypted, they cannot do anything with it. All right? All right. So for extra. So this is example. Let us show a private key ring table for Alice. For who? Alice. We assume that Alice has only two user IDs. This one and this one. We also assume that Alice has two sets of a private public key. So it has one set and one set. So what you do in here, look at here. The user ID is usually the email address. The key ID, we say what is the key ID? Maybe the first 64-bit of the public key. So AB13 up to 45, this is the first 64-bit of the public key. Public key is a public, that's fine. Same thing applies in here, right? And then you have in here what you have? The private key encrypted. So this is not the private key. This is the encryption of the private key. So if Alice wants to use, this is Alice? You said Alice? Who's this? Alice? Okay. So if Alice wants to use her private key to communicate with this person, what she has to do? Decrypt it first. Okay? And then you have the timestamp when it was created. So the ring is kind of like a table saved in your email system. Clear? Hello? Good? My friend still? Everybody's a friend of, are you my friend? Good. Alright, so that's what it is. Alright? Then in here we'll have format of the public key ring. What is public key ring? It's the public key of other people. Okay? So what I will have is a public key. So it's like this. It starts with a user ID, key ID, public key, producer trust, certificate trust, key legitimacy is legitimate, and then the time stamp. It's longer table for the public key. All right. So it has the user ID. We know what user ID is. The user ID is usually the email address. So the user ID is the email address. Then we have the key ID. As in the private ring table, the ID is first significant 64 bits of the public key. Then you have the public key, which is a public key. Then you have the producer trust. This column defines the producer level of trust. In most implementations, it can be one of three values: none, partial, or full trust. Okay, we'll talk about it, but you know, the produced trust could be one of three, right? Three values. Then after that, we have the certificates. This column holds the certificate or certificates assigned to other entities of this entity. A user ID may have more than one certificate. So you could have multiple certificates. Then you have certificate trusts. This column represents the certificate trust or trust if Anne sends a certificate for John, PGP searches the row entry of Anne, finds the value. We'll see in a second. Then we have the key legitimacy. Okay, this value is calculated by PGP based on the value of the certificate trust and the predefined weight for each certificate trust. So we have a certificate trust, value and we have a weight. So it will be calculated according to that, right? We are kind of reading the manual, how PGP is designed, like what we do, right? So your question, why is it designed this way? I don't know. They designed it, they tested it, it was very well tested, right? And there's versions, right? Every time they have, okay? So it's kind we are knowing how they are doing it. Okay, is it the best? Is it the optimal solution? Maybe not. That's why we have different algorithms, right? And thus we have always versions, improving all of that. So like Kerberos last week when we learned it, I mean we learned about Kerberos 4, but now there is Kerberos 5. There is a lot of things has happened, right? So we are reading how they are doing it. It's very interesting. Okay, it's a very interesting. All right. So, and sometimes, you know, because we are going through so many, still we have time, right? Still a lot.
Yeah.
We have half an hour, right? Yeah. So, because we go through a lot of these algorithms, myself I get confused. You know, I mean, in this so far we have learned how many different algorithms in this class? Maybe 20, 30, something like that. Okay, so everyone do it differently. So the whole idea you have to understand how it's done, understand the logic, you know, of it, try to analyze it. If you understand how the algorithm is spelled, then you could design a way to break it. So you have to know how it's spelled, okay, or how to protect it more. All right. So you are engineers in here. You're trying to think, or you're trying to learn how others designed or engineered all of these algorithms. All right. And you could do some analysis for that later. All right. So let's take example. Maybe okay. So in here, a series of steps will show how a public key ring table is formed for Alice. All right. So in here, for example, what it says in here, starting table. So that's the starting table. So now, for the public key, you have to learn it. It keeps growing. So for example, I mean, how many people I know I could communicate with in the whole world who have emails? 1 billion, right? 2 billion, 3 billion, right? I don't know how many people. Do I need all of them? No, I need the people I deal with. So when, for example, I have to deal with a person, okay, for the first time, with security, with PGP, I'll add his or her public key to my tables. So the table keeps growing as I use people, right? If I try to communicate with somebody, I don't have his public key. What should I do? Get the public key. From where? From other people who I know dealt with him, for example. I trust. Right? Or from where he posts his public key. From some certificate authorities, right? Alright, so what's the idea in here? I'm trying to build the table, right? Through what? Through trust. Other trust. So if somebody I don't trust and he gives me a public key for somebody, what should I do with it? I don't trust it, right? And if a person I fully trusted and give me a key for other person, I use it. If 3 people I partially, or 4 people partially trust, they give me the same key, what should I do? Maybe trust it, because 4 people. Yes, I trust of them partially, but 4 partially could equal to 1. Or, you know, depends, you understand? So in here, I'm trying to give you the general idea what we are doing in here, right? It's like building the trust. So in here, for example, Alice, user ID is Alice. The key ID, we said is taken from the public key, first 64 bits from the public key. And this is the public key. In here, what does it say? Producer, trust. F. What does it mean F? Full. It means full, right? Full. There is no certificate trust, and the key legitimacy is full. Okay. There is no timestamp. Okay. So we start with one row. Alice herself, as shown in the table, as you show this table, okay, use N, none, P as partial, F as full for the levels of trust. For simplicity also assumes that everyone, including Alice, has only one user ID. Then we come in here, right, So Alice in here has issued a certificate for herself. Okay. Alice, of course, trusts herself fully. The process level of trust is also full, and so it is the key legitimacy. Although Alice never uses this first row, it is needed for the operation of PGP. Now, after that in here, what will happen? Alice adds Bob. So she added Bob. So that's herself, that's a Bob. The key ID, the public key, the trust full, and legitimacy full. So it could have, she had this key directly from Bob. She met Bob, Bob gave her the key. So she put it in the table, and it's a full trust because she knows Bob gave her the key. Right? Bob gave her the key. So let's see here. So now Alice adds, okay, and now Alice adds Bob to the table. Fully trusted Bob. But to obtain his public key, she asks Bob to send the public key by email as well as his fingerprint. Alice then calls Bob to check the fingerprint. So she called. So Bob sends to her. She called. Did you send me this? Okay. Yes. Is it fully trusted or not fully trusted? Fully trusted. That's why it's a fully trusted. Then after that, Ted is added. But look at the Ted added full trust. How did she know about it? From Bob. And because she fully trusts Bob, it became, the key is very legitimate and full trust. Okay? Very legitimate and full trust. Okay? So let's say, in here, the only way I understand what happened, I have to read what is the scenario. This is a scenario. So I have to read the scenario for you, the author put. Okay? So now Alice adds Ted. Alright? To the table. Ted is fully trusted. However, for this particular user, Alice does not have to call Ted. Instead, Bob, who knows Ted, so Bob knows Ted's public key, sends Alice a certificate that includes Ted. So Bob sends a certificate to Alice with the key of Ted. Okay? So Alice trusts Bob. Bob sends the public key for Ted. Certified. Then Alice should trust this key. Why? Because it's coming from a certified source. See how is it built? Okay? Why you are doing all of that? To avoid using certification authority. Third party. Right? Okay? Somebody will say, why? Let's use certification authority, it's faster. Okay? But that's how it is, right? That's how it's designed, right? So now we understand how that was built, right? Okay? Then we go to the next one. Now we're adding who? N. Okay? So now Alice adds N to the list. Alice partially trusts N. So Alice, where is Alice? Alice partially trusts N. Okay, but Bob, who is fully trusted, sends a certificate for N. So Bob sends so Alice partially. He sends a full certificate for N, then the key will become fully legitimate. And so on and so forth until the end. Okay? So it's like, keep building the table, getting the keys from the people you trust or partially trust, then you assign the trust level until the end, okay? The idea in here that you have to have a public key and you have to, this public key to you in the table, is it fully trusted, partially trusted, not trusted? That's the whole idea. Okay? Got it? Okay? So just follow the scenarios in the book. This is just a scenario. And there's assumptions that we have to follow. So then John added until the end. So let's talk about the trust model in PGP. So trust model in the PGP. So as you see in here, Alice, I mean, this is from the tables. So Alice, let's take the code. So this green fully trusted entity, the yellow is partially trusted entity, and I'm not sure what this orange may be, untrusted entity. So Alice, for example, fully, Alice partially trust Anne and Mark, okay? She does not trust Helen, she does not trust Duke, does not trust Kevin, John, and fully trust Bob, Ted. Why trust Bob? We said from the first example, because Bob sent the public key and she called him. Is this a real public key? So trust him 100%. Okay? Okay, and okay. And this is for the Alice, right? And so on and so forth, right? In here is not clear if a trust or not trust. So in here, so X has legitimate key. What does it mean, X? When you see the key in here, you see it has a legitimate key. So there is legitimate key. Here does not have a legitimate key. When you say X to Y, that means X introduced by Y. X introduced by Y. So for example, in here, John was introduced to Alice by Anne. Okay, by Anne. X question mark, X introduced by unknown entity. So in here, for example, you know, Duke was introduced by unknown entity. All right. So you're trying to build the trust model. Okay, so it may become necessary for an entity to revoke his or her public key from the ring. Okay, you have a key in the ring. You need to revoke it, remove it. Okay, it was like compromised for any different reason. This may happen if the owner of the key feels that the key is compromised, stolen, for example, or just too old to be safe, safe. So extracting information from rings. Again, rings is like tables, right? So for example, in here, what you have in here, this is the private key ring, and this is the public key ring. So you're looking for Alice's user ID. Okay, you're gonna look at the user ID here. It comes in here. Then you're gonna get the Alice's key ID. Then you're gonna get what? You're gonna get the private key. We said the private key will be saved, encrypted. So what you have to do, decrypt it in a certain way. How you decrypt it? There is a decryption algorithm. There is a passive phrase. You have to pass it to hash. Hash will create a digest, and that will be the key for this decryption, and that will give you the Alice's private key. The Alice's private key. Okay. So that's what you need to get. What you need to get the Alice's key ID and the Alice's private key. Good. And this could be generated by keystrokes. So the keystrokes could generate the session key. All right. It could be random session key. For the Bob's user ID, so you have Bob's key ID. And then you have to get the Bob's public ID. There's no decryption because save not decrypt. Right? So what for this process in here, let me go in here. Here. So what I have to have? I have to get the shared session key. I have to get Alice private key and public key, and Bob's what? Public key. And I get them where? Like this from here. So this is session key. It will be randomly generated. This is the Alice's private key. Okay? And this is the Bob's key ID and Bob's public key. And what is this? This tables and page B. So PGP basically has how many tables? 2 tables or rings, public and private. Okay, and that's how we generate that. Okay, extracting information at the receiver side. At the receiver side, what you need at the receiver side? Again, I need the passphrase again. Okay, and I need the POPs ID, encrypted session key, right? Actually, that's what I need in here. That's after.
Yeah.
I need the POPs private key. I need the session key and the Alice public key. Same thing. So I have the passphrase which was sent, okay, to the hash and do the decryption. I get that private key. That's the private key, and encrypted session key. I get the session key, and then I get the private key. So just as how the 2 tables, you have to get the information from the tables. Public and private key. PGP packets, when you look at the packets, PGP packets, because what we do, the data, put it in PGP packets. So PGP is kind of a level higher than HTTP, right? Okay. Okay. So format of the so for example, this is old format and new format in here. If it's 0, old format, new format. 1 tag 1 byte, length 1, 2, or 5 bytes. So 64 different packet types. There's 64 different packet types. Okay. So the packet types. Number 1, session key packet encrypted using public key. Or number 2 is a signature packet. Or number 5, private key packet. Or so there's many different types of packets. Okay. Literal data packet. So the data itself, okay, in here, okay, tag 1 byte. Okay. If the tag 11, then you have the body length. How long is the body? Then the model, the length of the next field name, timestamp, and literal data. This is the data. The real data will be here. So message file or keys will be inserted here. Okay, compressed data packet. If you have a compressed data packet, so the tag will be 8. That's the length. That's the compressed method, zip or whatever, and then the compressed data. Okay, but the compressed data will be, you take the data, you compress it, and you put it in here. In here, the encrypted data packets. So you are sending the data packets. Okay, so the length and what you'll put the data or the packets, you encrypt them. Okay, using the shared session key, you put the encryption in here, and then you send it. All right. Then you have signature packet. You could send with PGP a signature packet. So the tag will be number 2, the length, whatever the length, the version, the length, the signature type, the timestamp, the key ID. Okay. The key ID of the timestamp will go to the hash as input with the message file. Okay. And they will create a digest, and then we encrypt the digest, and this will become the signature. Becomes a signature. All right. Some signature values. So, for example, if it's 00 signature of a binary document, message or a file. So this is the value of the signal will explain what kind of signature you are having in here. Session key packets. So tag 1, the length, the version, the key packet, key algorithm, and then symmetric key algorithm, the session key, the checksum, all of them will be encrypted and send an encrypted session key. Public key packet, and this is the different packets you could send with PGP. Okay, that's the structure of it. Just you have to study it. Cannot help you. Okay, you cannot memorize it even. Okay, just you have to know how it works. Okay. This is for user ID packet. If you need to send user ID, tag 13, the length and the user ID. All right. For PGP messages, okay, you have tag 1. So this is the session key packet, and then the encrypted session key. Okay, that's tag 1. Tag 11, it will be inside tag 8, inside tag 9. Right, and inside we'll have them. So if you need to know tag 8 and 9, we will explain them. And here, this is 8, which is a compressed, and 9 is the encrypted data. So. Okay, encrypted, compressed, and anyways. This is the signed message, the certificate message, and so. So you just have to take a look at how you can't memorize them. I'm not asking you to memorize them. Just know how PGP works, how the buckets are works. Okay. So to summarize, what we are trying here to do, to using PGP for email. Okay, for email. So we could send the plain text. That's no PGP. We could compress it. You could encrypt it. You could use check for the integrity, different way. For that, for all of this, you need what kind of keys? You need two rings, two data. You need the public key of the recipient, and you need a private key, a pair for each user you're gonna send to, and you need to issue also a session key, right? You're gonna use many algorithms. You're gonna have one algorithm for compression, one algorithm for hashing, one algorithm for exactly. So all of this, sender and receiver has to share them. All right. So the sender, when he send all of this, has to tell the receiver, yes, I'm sending you a data, but the data we have used so and so and so and so. All right. It could be signed, not signed. There is, different levels of security. All right. And this is security at what level? Application level. At the application level. For what? For securing what?
Pretty good BGP, pretty good privacy.
Securing what?
Email.
Email and files.
Fine.
So you could use PGP to secure files in your system, okay, and to secure email. All right. So the next one, can we finish it in 3 minutes? You think? Even much more complex than PGP. It's mine. So what I will do, I'll leave it for you to read it. Okay. I'm gonna go to next week to the transport layer, then the network layer. If we have time, we come back to SMI, but it's another example for one of the algorithms. Thank you.